Okay, so we are continuing with the second hour. Now what we have done, we have first derived marginal density, you may say, of this joint density a few minutes ago. Now we would like to derive the joint density of these two random variables by using this conditioning, let's say, factorization of this. Now, how can I derive this? This is the question mark. So let me write this. I would like to find the distribution of this, x2 given x1. If you wish, I can call this another random variable z. Okay? So please think about it like that. As soon as I condition this random variable, don't think about this random process. This is something very general. By something else, essentially there is an update. There comes an update on x2 and I have a new random variable with new density. Okay? So conditioning results in a new random variable. That is the idea. Okay. So how can I find this distribution? Distribution of z, you may say. This conditioning idea. So let me write this. Now x2 is equal to a times, a is the random quantity, just to mention, t1. Okay. So I am conditioning it with x1. This is a times t1. Conditioning means I know this random variable. So let me write it like small x1. Capital X1 is equal to the small x1. Conditioning. Okay. So how can I find the density of this? That is the issue. Conditioning. Okay. Well, how about this? Let me rewrite this, even though this is trivial. x2 is equal to a, so this is x2, there should be t2 over here, isn't it? x2 is equal to a times t2. x1 is equal to a times t1. Okay. So let me write this like this, t2. Instead of t2, let me write something like that. This is always valid by cancellation. And x1 is equal to a times t1 is equal to x1. So what do you think? Now in this conditioning event, okay, this becomes, again this notation, small x1. Okay. So as soon as you make this observation, observation is random variable x1 is equal to this value. For example, this is random variable, which is taking values in between 0 and t1. Let's say t1 is equal to 1, as in this case. So it's taking values in between 0 and 1. So I have made an observation. I am telling you that at time t is equal to 1, this takes the value of 1/2. Okay? So I'm on this realization. Nature picks this realization. No one tells me. But later on I make an observation. And then from this observation I can maybe make some deductions. So process is something like this. Nature, let's say, picks a value of tau. Nature doesn't tell me. Then this picked value becomes a parameter of this function. Then you have a function. Okay? This is called an experiment, random experiment. Now nature can pick these values from this distribution, and you have infinitely many lines like that. Okay? So I make an observation. This observation, as we have said, becomes at this time, it becomes a random variable. Again, it's distributed in between 0 and 1, uniform distribution, and so on. It becomes like that. Now I have two observations, and the issue is this. If I know the value at time t1, what can I say about the value at time t2? If you know it. Okay? So you see that what is this conditioning density? Well, this conditioning density, if you know the value of time, value of x1 at time t1, actually you can identify the realization, isn't it? You can identify which realization you are on. So once you identify the realization, you are done in this simple example. So you see that this is equal to this, let me write it just for clarity. This is x at t2 given your observation at t1 is equal to small x1. So this is x2 is this, x1 is this. So what is this one? This is a delta function because it can only take this value. Okay. So if you know that you are on this realization at a later time, because this is increasing linearly, you just multiply it by t2 over t1, okay, to get that other value. That is it. So is this clear? This is the conditional density. So if I sketch this, let me use this part. This was something like this, marginal density. This was first order distribution. Now how about my second order how about my conditional distribution? My conditional distribution is okay. So this is, again, as I have said, this is a little confusing. So what's the variable? Variable is x2. Actually, this is x2 random variable updated after this observation. Okay. So my variable is x2. What is x1? x1 is actually a numerical value. Okay. x1 is my observation. It's a numerical value. So whatever that numerical value is, I have this impulse. These are also numerical values that I know. This is by conditioning that I know. And the weight of the impulse is 1. Okay. So the density becomes, again, an impulse. So this is the conditional density. This is the marginal density. So I should multiply those two. So let me write it over here then. xt1, xt2, x1, x2. So I have 1 over t1 times f of a. What was this? x1 over t1. So uniform, this is this part, uniform distribution. Okay, times. So this is uniform in between 0 and t1. This is from part, let's say A. This is our first order density. Now times delta x2, x1, t2 over t1. Am I right? For example, if t2 is, as in this drawing, double of t1, x2 is also doubled with respect to x1. That is it. Okay, so how can I sketch this? So this is a density in one variable, x1 only. Now this is a density in two variables, x1, x2. Let me have x1, x2 over here. So how can I sketch this? So I know the marginal density is for x1, uniform distribution in 0 and t1. Okay, so it takes values over here. I know the marginal density for this one. It takes values in 0 and t2. So I should be having something like this, perhaps. Okay, so how can I draw this? Well, so let me write. Let me move this. Let me change this. So this is my line. x2 is equal to x1 times t2 over t1. Okay, so what do I have? Let's say that I'm trying to sketch a point of this. So give me some x1, x2 values, this one and this one, which results in a non-zero density value. So because of this impulse function, everywhere is equal to 0, except on this line. Maybe I should draw these impulses a little smaller. Okay. So on this line, I have only probability, density function, non-zero values. Okay. Otherwise, it's all 0. Do you see this drawing? So when x2 is equal to x1 times t2 over t1, this is this line, on this x1, x2 plane. Okay. I have this. So this point is t2, t1 point, t2, t1. Okay. So this is an allowable point. All other points are this. Okay, so that would be our density function, and these heights are equal to each other, you may say. Okay, if we call it heights, but it's an impulse. So this is the location of this, because as you see that this is just constant. This is just uniform distribution, a constant value, and this is like this impulse response is setting whether this is equal to 0 or not, essentially. Okay, I have that. So this is called the second order density. So this concludes the derivation of second order joint p.d.f description for, let's say, random slope signal. Okay. So let me write some notes. So this is the end of this example. Note number 1. Nth order joint p.d.f description. Well, nth order joint p.d.f description. The full joint p.d.f description of a random process is given for, let's say, n samples. Actually, this is for all n. Say T1, T2, Tn. That is, we need to find density function, joint distribution of all of these. Actually, this is, you can think, quite tricky. Why it is tricky? Well, I should do this for all n, first of all number of samples, and for all T1, T2, Tn, let's say, vectors. Okay? So, but that is the best thing we can do. If you are interested in the probability description, you should be finding nth order p.d.f description. This is the best thing, this is the best we can do with the random processes. Actually, what we do is we reduce the description of random processes to joint p.d.f description of random variables, as you see. Am I right? So I sample this random process at different times, and I look at their distribution. But you can see that this will be getting more and more difficult. If I get more and more samples, now I'll be having more and more difficulties in these type of discussions. So let me write a few notes on this. Number 2. if we have nth order p.d.f description, n minus first, let's say something like this, n minus second, and other lower ordered descriptions can be immediately found by, what should I write over here? A word, a terminology in probability by, no, not the other one. Who wants to buy a letter? Marginalization, exactly. Okay, by marginalization. Am I right? Because if you know this, if I integrate this over xn, the last variable, I get rid of that, so I get n minus first order description. Okay? So this is good. Yes. Exactly. So from smaller ones to the bigger ones, we do the conditioning because it helps us. I'm taking into account what we know earlier. But this is, if you know somehow the nth order description, this is good. Maybe I don't need to find the first order description if I know the second order description, isn't it? It's just embedded inside, okay? Which is good to observe. So this is very valuable. If we have nth order description, we can by marginalization. Okay, so first order description is, let's say, embedded. Biraz kötü. I'm writing it poorly, sorry. Inside of second order joint p.d.f description. Okay, so I don't need to maybe do dual work. So what else? Number 3. Unfortunately, for many processes, finding p.d.f description is too difficult for high orders. We simply try to work out first or second joint p.d.fs in many cases. And sometimes you cannot even derive these second order p.d.fs. As you see, this is a very simple example. We'll be having more examples coming up. This will be more difficult. So let me write. In the random slope example, like that we have studied, the joint p.d.f was easy, or let's say is, because it's always, is easy to find, since the process has essentially single degrees of freedom in some quotations from related with the random experiment. That is selection of A, or the slope parameter. So So as soon as we observe, let's say x1 is equal to xt1, we can identify the realization of, we can maybe actually uniquely identify, because as you see, there was a Dirac delta. As soon as I observe a realization, conditioning on that, I can predict the rest. So as soon as we observe this, we can uniquely identify the realization of the random process and samples, let's say T2, at T2, at T is equal to T2, let's say at T is equal to T3, etc., can be deterministically written in terms of x1, like we did over here, like we did over there. x2 is equal to x1 times t2 over t1, okay, like over here. So this is due to the simplicity of this example. There was only one random variable, this is the slope, random slope signal. So as soon as I make an observation of it, conditioned on that, I can make predictions for all times. Okay, that is it. What else? Let me see. Let me also write that. Of course, in the random slope example, x of t at t is equal to 0 does not help us to identify the slope t is equal to 0 slope parameter. So you see that there can be some special times good for identification, there can be some special times bad for identification, etc. So in this simple example, there was only one bad time. If you observe the signal at t is equal to 0, I mean it's always 0, so you don't know anything about any other thing about this outcome of that random experiment, because all realizations are passing from 0, as we have said before. Now, let me have an example. So what is this example? So let's calculate first order p.d.f. by marginalization of second order density of random slope process. Okay, this is just an exercise. So this is the density. Let me erase this. Let me put a star over here. So let me say solution just to be clear. So the second order density is at, this equation star. Okay. So what should I do? So I will integrate that density. This shouldn't be very difficult. And I should get my result. So let me have this density of x1. This is the issue. So if I want to find this, what should I do? So this is equal to, let me write x1, x1. So I should integrate this joint density x1, x2, x1, x2 with respect to dx2. Am I right? That is it. So if I insert this over there, so let me write this like this. Okay, let me write it for simplicity again. I have 1 over T1, f of A, this is uniform density, x1, T1. So just remember, A is uniform 0, 1 for the record. Okay, at the beginning of the problem we have defined this. Times delta x2, x1 with some scaling. So how do you integrate this? Well, what is the integration variable? X2. So this is the integrand. I should put this integrand over here. So you can see that if I integrate this, this integral will be coming over here, and I have dx2 over here. Am I right? Okay. So what is the final result if you integrate this? So x1 is, so you should be always careful with the, this kind of integrals. When you look at this integral, what is the variable of integration? Obviously, x2. So for the sake of this integration, just be careful. This is the variable. So whatever you have over here is just a constant for the sake of this integration. Okay? So think about it like a numerical value. So as x2 ranges from minus infinity to infinity, it will hit this numerical value, whatever it is. Then at that value, it will be equal to 1. Okay? So this will be equal to 1 at that fixed x2 value, and there is nothing else. So integration result is just this part, 1 over T1 fa x1 over T1. Okay, this is the end. That was easy. Okay, just be careful in the integration of this. Now let's look at the other one. So this is the second one. So what should I do? Again, I'm integrating this. So let me write this one more time. Let me write it over here, the joint density. 1 over T1, f of A, x1 over T1, delta, I should write x2, x1, T2 over T1. And this time I'm integrating or marginalizing with respect to the other variable, isn't it? x1. Okay. So this is my joint density, marginalized with respect to the first variable. So I'm left with the second variable. Okay. Now how can I integrate this? This is a little bit tricky. Actually, this is the reason that I have mentioned this. So how do you do this? You just trust on your basic calculus skills. Now you say that I will be doing a change of variables. You call this u. Okay. So let me write this u. U is equal to x2 minus x1 t2 over t1. Okay. If that is u, I need an integral with du. Okay. So I'll be writing something over here, but this will be du, and sorry, this will be u, and I need du. Okay, let me pull this x. Okay, the integration variable is x1. Okay, so x1 is the variable. These are constants right now. x2, t1, t2 constants. So let me pull this x1 over here. Move this x1. x2 minus u, t1 over t2. Am I right? Move this x2 minus, I think it's correct. Okay, so instead of x1, I'm writing this. T1 over T2, this. Am I right? Then du, this was good. How about dx1? dx1 is minus dx1 is d t1 t2 du. Am I right? That is it. So if I have this change of variables, now u is equal to this integrand. This will be taking, okay, more issues. How about this integral limits? You should be careful. Yes, this should be interchange. Because when x1 is equal to minus infinity, what's the value of u? Plus infinity. When x1 is equal to plus, I think you get the idea. Okay. But I don't like to see plus infinity over here, so I prefer minus infinity and plus infinity over there, and I don't want to have this minus then over there. Okay, do you agree? So this is f of a, x2 minus u. I'm writing it one more time. t1 over t2, t1, delta u, d, let me do a cancellation, just for space saving, du. So I have just cancelled this minus by interchanging these limits. Do you agree? Okay. Now, do you think this is an easy integral? Well, whatever it is, again, this will be equal to 0 almost everywhere. So when this u variable is taking the value of 0, then this will be evaluated at 0, and that will be moving out of this integral. Okay, that will be it. Otherwise, it's always 0. So do you think u can take the value of 0? It can take the value of 0 because 0 is in the integration interval. So what do I have? So if you check this, now I'll be just evaluating this at u is equal to 0. That is it. Fa, when u is equal to 0, x2, t1s cancels, t2, that is it. Do you agree? When u is equal to 0, t1 cancels this, t1, I have t2, t2, that is it. So, very good. Because what do we have? At the end, we get uniform distribution, isn't it? This was the uniform distribution. As we have said, this is the uniform distribution for x1 variable, random variable. This is the uniform distribution for the x2 variable. Only difference is that, the uniform distribution's limits are changed. Okay? That is it. Why am I telling you this? Just be careful if you are doing these kinds of integrations. Now, you have taken so many courses with Dirac delta functions, so on. Just be careful. Of course, if you have more experience in these kinds of, operations, maybe you can remember this. Let me write t. This is equal to what? Do you remember? Things like that. Delta t. Again, if you remember such things, the properties of Dirac delta functions, you can write this maybe instantaneously. But if you don't remember this, that's okay. Do a change of variable. Okay? So what do I say so? For example, forget about this. Integration variable is x1. So x1 corresponds to this t. A is t2 over t1. Okay? So this is equal to delta of variable scaled by 1 over a. Okay? Things like that. So that multiplication t1 over t2, as you see, reciprocal of this. 1 over a. Again, you see the absolute, isn't it? You see here absolute. Do you remember we have changed this -1 plus absolute? Okay? They are all reflected. But if you don't remember this, don't worry. You don't have to remember everything. Then just be careful. Which one is integrated? What is u variable? Do this patiently and you will get the result. Okay. Okay. Now, this is our random slope example. Now I want to do, let me see. How much time do we have? Okay. So let me see. Partial description of random processes with moment descriptions. So I will start this, even though this is a very simple topic, and then we will continue in the next hour. So in many problems, finding the density description is too difficult or at times infeasible. So you don't even attempt. Because this mapping is too complicated. Okay? Our mapping was very easy, it was just a single parameter. Okay? In many problems, the density description is too difficult or at times infeasible, let's say, to compute. For such problems, we use moment, or this is also called partial description. Partial description of random processes. Okay. So what do I mean by this? You will see. Moment descriptions. So x of t is the random process. So let me write first order, again there are orders, first order moment description. So this is simply the expected value of, I can use both, let me use both notations, capital X of t. Okay. This is called the mean function. You will see this is something very easy to calculate in comparison to the p.d.f descriptions, because you will see the main property of expectation is that you don't need the densities of x1, x2, x3 explicitly to calculate these expectations. I will show what I mean in a second. But let me before that the second order descriptions. So this is expected value of this. This is called autocorrelation function. And we have Cx k1, k2. This looks complicated to write, but as I have said, much easier to compute. So the second one is called, do you remember what this is called? This is called covariance function. Okay. So what are the random quantities over here? For example, if I'm evaluating this at, this is a function at changing by t1. If I'm evaluating at t1, then this, I need the density of xt1, isn't it? So if I am calculating this, I need the density of this, and so on. So similarly for the covariance function, I need this. So this may look complicated, but it's not complicated. Essentially, you have a random variable over here. You are calculating the mean value of that random variable. That is it. Okay? So please remember, okay, let's go back. Example, random slope. Because this is so easy. Random slope signal. find, let's say, mean and autocorrelation function for random slope signal. Okay, so I will only do in this hour, the on the mean function. So this is the first order description. Now I'm assuming that this is an ordinary function of, let's say, t1 for the sake of clarity. Ordinary function. There is nothing random about this. But this function denotes the mean value of the distribution. Do you remember we had first order description, second order description for the random slope signal? So this is the uniform distribution, first order. So the mean value of that uniform distribution will be calculated. Okay, at t1. So you can say that, okay, this is not easy because I need to find the density of this xt1. Then you say that finding the density of the description is too difficult. Okay, so how does it work? I mean, it's not good. But then you do the following. This x is defined as, this is the random process description, a times random quantity is this, a times t. So this is the overwriting property of expectations. This is the important property of expectations. So as soon as you write inside of this, this requires a proof, but this is central to expectations. A times t1. Now you can evaluate this with respect to a. Do you see what I mean? This is something that you know very well, but this is critical, as you see. I need to find the density of this. So I don't want to find the density of that. I know that this is equal to this, or this random variable is generated from this relation. I put it over here. Now I see that this equality of these two expectations. This looks trivial to you, but this is a big deal. This is change of measure. Actually, you change so many things. Okay. So how do I calculate this? Well, t1 is constant. Expected value of a times t1. A is the random quantity. Okay. So what was A? A is uniform distribution in 0, 1. In this random. Okay. So this is t1 over 2. That is the end. This is 2. Okay. So you see that this is the reason moment description is easy. Because I don't need the density of these samples. Maybe I can use the definition of the random process to evaluate those expectations. Okay. That will be very useful for us. For the second order description, do you think it's also easy? Now I have a times t1, a times t2, a squared times t1 times t2. Move t1 times t2 out of integration. So this is the expected value of a squared. Even though this requires a joint density, now density of a is sufficient to find this. So very easy, as you see. Okay? But we will continue from this point on next hour. And that's it for today.